So you guys might know already Arjan, which is our v64GC core that has been recently taped out at 1 gigahertz. By the way, this guy has one FPU, which means that it can achieve up to 2 gigaflops in double precision floating point. And then we thought, how could we push it further than this? And that's the reasoning behind ARA, which also works at 1 gigahertz, but can achieve up to 8 gigaflops double precision floating point. And you can see here that the interface Arjan ARA is pretty light. Basically, Arjan pushes instructions to ARA that answers them back, and they share some memory translation interface. So to talk about all this, about performance, it's interesting to bring the roofline plot, which is a measure of the peak performance that can be achieved as a function of the operational intensity, which is measured in operations per byte. And this measures the amount of data reuse of the algorithms. So based on the operational intensity, there are two regimes, the memory bound and the compute bound regime. In the memory bound regime, the functional units, they are starved, they keep waiting for memory. And because of this, they cannot be fully utilized. Whereas in the compute bound regime, there is enough data reuse and they can be fully used. So we want to be in that region. We want to have a performance as high as possible. And this for ARA means that we are looking for an operational intensity higher than 1. We chose to implement ARA as a high-performance vector processor in GlobalFoundries F22FDX process, and this was my master thesis and also a few months of my ongoing PhD studies. And as a part of the POPE project, our plan is to open source it as usual. So this talk is meant to be a snapshot of ARA, the challenges we faced, the results we achieved, the insights we gained by developing this vector processor. But why did we choose to implement ARA as a vector processor? Well, vector processors, they exploit what is called SIMD, single instruction multiple data architecture. Simply put, one single instruction encodes a long set of micro operations, which means that you need less instructions to encode same operations. So you spend less time decoding instructions, you have a simpler control, less energy spent in fetching and decoding. When we talk about SIMD, there are two major lines of thought. The packed SIMD, which is what is generally known as just SIMD, which would be used, for example, by ARM's Neon or Intel multimedia extensions. In this kind of architecture, the amount of data that is handled per cycle, per instruction, is fixed. And there is also the vector SIMD approaches, whereas the vector length is configurable. Vector SIMD is also known as Cray-like SIMD because it was Cray, back in his Cray 1 machine in 1977, that first presented this kind of architecture. More recently, we have Huasha, that was presented yesterday, by the way, which is, however, a vector fetch architecture. It's a bit more complex. Well, because the vector unit itself is responsible by fetching and decoding its own vector instructions. Huasha achieves 64 double precision gigaflops in TSMC 16 nanometers, and in terms of power efficiency, 40 gigaflops per watt in ST's 28 nanometers FDSOI. And what's the role of RISC-V in all this? Well, RISC-V has its V extension, the vector extension, that is pretty active lately. Basically, in every workshop, there is a new iteration, a new version of this extension. And ARA was based in the version 0.4 draft. Simple reason, it was the version that was available back in February when I started my master thesis. However, because ARA and the V extension, they developed concurrently, there was some kind of feedback between them. And this is why we are not fully compliant to the version 0.4. For example, we do not support fixed point or vector atomics. It was not our focus. And we also do not support the fully set of type promotions that was expected in the version 0.4, because we've seen the high hardware cost that they incurred. And this is fun because it was eventually dropped in later revisions of this extension. Just as a parenthesis, here you guys can see Zurich. Looking forward to see all of you guys for the next workshop in a few months. And now we can dive into ARA's microarchitecture. We do a bottom-up approach. We start with the main data path elements, the FMAs. So the most complex operation this block executes is the mask FMA instruction that has 4 source operands and 1 destination, the 5 of them 64 bits wide. The FMAs are pipelined at 5 cycles to meet the 1 GHz constraint. And here we chose to control the FMAs in a way that the 4 lanes, they operate in lockstep, which means that we only have 1 control and this control is amortized and is reused for all lanes. So each lane takes 64 bits operands from those 256-bit queues. So basically the number of lanes determines the buffer width. And also in the output side, the output of each FMA is concatenated and written to this result buffer. A higher view of ARA, we have those queues. In the input side and the output side. Why are they there? They are there to allow us to hide some latencies and some bank conflicts that might happen on the vector raster file. That is something that we will explore in a few slides. So we have one queue for each operand of the 4 lanes, which means that I have 10 queues. 4 shared between the FPU and the multiplier, 3 for the ALU, 2 for the load store unit, and 1 for the address generation, which is basically used for scatters, gathers, and the vector raster gather instruction. Yeah, we have something similar in the output side, 1 queue for each multi-lane data path unit. Now we'll talk a bit about the vector raster file, which is the core of this and every vector processor. So it's organized like this way. The width of each bank is 256 bits. The reason this is basically constrained by the number of lanes, and we have 8 banks. The reason for this is that the most complex instruction, the instruction that reads and writes more operands, the masked FMA, touches 5 banks per cycle. So with 8 banks, we would have a banking factor of 1.6. And now we'll see how the vector registers are organized in this memory. So let's suppose that we have 4 vector registers. So the first 4 elements of the first vector registers, they are in bank 0, the next 4 in bank 1, the next 4 in bank 2, and so on, until the vector 0, this logical entity, uses 1/4 of the vector register file. And something similar happens with V1, V2, and V3. So please note that all the first elements, they are all in bank 0, the first bank. And now we can talk a bit about the overall architecture of ARA. You can see the 8 banks, the operand queues, the functional units, and the result queues, and some control. So we have this interconnect that goes from the 8 banks that we just seen to one of the 10 operand queues. It is registered for timing to meet that 1 GHz constraint. And we have another interconnect that goes from the 4 functional units back to those 8 banks. And because we chose to implement our vector register file as one read-write SRAM banks, we need to arbitrate between all those access to the banks. And this is the role of the vector register file arbiter. It's fixed priority for our simplicity. We chose to have the mask has a higher priority than the operand A, higher than the operand B, higher than the operand C. And the writes, they have a lower priority than the reads, unless the output queues, they are full. This is to avoid head-of-line blocking. And now to wrap it up, we will go through the execution of a single instruction, this FMA instruction. We will take a vector of length 256 that should take 64 cycles, ideally, to run. So in the first cycle, the operand request block is requesting the first elements of the 4 source operands. They are all in bank 0, and because of this, only the mask will actually access this block, and 3 access will stall. However, because of the queues, in the next cycle, the mask will be able to access its next 4 elements, and only 2 requests will stall on the vector register file arbiter, and so on. In the third cycle, only 1 request is stall. And after this cycle, the operand requests are aligned in a way that there are no more bank conflicts in this side. The first FMA is issued at the 7th cycle, goes on, and the first results are written in this cycle because of the FMA latency. Please note that in this cycle, the first results of the FMA are written back to the bank. bank 0. So in this case, we have another bank conflict. But because of the queues, we can still maintain this throughput. In the next cycle, we get a grant for the write. And from this cycle onwards, actually, we can see this pattern of we are always accessing 5 banks. And this continues until the end of execution. So this 64 cycle instruction takes 70 cycles to execute, an FMA utilization of 91%. And a final point about the architecture of ARA, we also support reductions, for example, which are instructions that goes from vector sources to scalar destinations. For example, this dot reduction that is triggered by a multiply add on a scalar result register. And we chose to implement this reusing the FMA. We have a feedback path from the result of the FMA to the adder input. However, because the FMA has some latency, this creates some problems we talk about with this example, the reduction of a 64-element vector. In the first phase of this reduction, we can actually issue one partial sum per cycle. So we have a phase that has a 100% of utilization of the FMA. This phase takes 16 cycles. However, because the FMA is pipelined, we actually have one result per pipeline stage per lane. Have 20 partial results that must be merged together to have the final reduction result. So to do this, first we merge the 5 pipeline results. We have to do this by using a logarithmic approach, and this first phase takes 17 cycles. And after this phase, you only have 4 partial results, 1 per lane. However, please note how many bubbles there are in this zone. The utilization of this phase of the reduction is very low. And then the next cycle, the partial results of each lane are merged together. First 2 lanes, 1 lane, until the final result is written. Again, lots of bubbles. So, even though in the first zone have 100% utilization, the overall utilization of the FMA for this reduction is only 36% because of this reduction tail. However, please note that this tail does not depend on the size, on the length of the vectors, but only on the latency and the number of lanes. So a few solutions that we could use to improve reductions would be, first, to fill all those bubbles with operations for the next vector instruction, which would require just a more fine control. And in this case, the utilization would go up to 77% in this case. Or spend more hardware with an extra adder that would be responsible by merging all the results. And in this case, the FMA, the utilization would go up to 100%. And now we will dive into the benchmarks. So here we are back to the peak performance, to the roofline plot. We have those zones, the memory bound, the compute bound zones. The performance we are going to measure, they are going to be in this zone. However, we want to measure, if possible, at that zone. We want to measure performance that are higher than the peak performance of Arjan. Can we achieve 8 gigaflops? So, can we have the 4 FMAs working at 100%? We will analyze performance with 3 kernels, a XP, which is heavily memory bound, and 2 compute bound kernels, the convolution and the matrix multiplication. So, to do this, we analyze performance with a cycle-accurate RTL simulations, and we ignore some initial cycles for instruction fetch and the configuration of the vector unit. So we start with a memory-bound kernel, with the XP kernel, which does this, A times X plus Y. To do this, we do what's called a strip mining loop, which is breaking a problem of length, in this case n, into pieces that fit into the vector processor. So the operational intensity of the XP. To calculate this, you have to load vectors X and Y and store the vector Y back. So you need 24 n bytes of memory transfers, and you have to do n FMAs, which is 2n operations, which means 1/12 operations per byte. So the XP is heavily memory bound. We will not achieve 8 gigaflops with this kernel. And how close are we to the performance limits of the XP? So in this graph, you can see the performance we achieve as a function of the vector length. Here the limit is around 0.67 operations per cycle. And we tend pretty close to this limit. And please note that if we had a wider memory port, we would be able to increase this performance because we are in the memory bound zone. You can also note that with shorter vectors, we actually have a performance degradation, and this is due to scalar instructions that have to run in Arjan for pointer calculations, and also the limit number of parallel vector instructions that can run in ARA. Sorry, and now we go to the convolution, which are the first of our compute-bound kernels. Convolutions are pretty used in convolutional neural networks. That's why we chose a small kernel, a 3x3 kernel. And in this case, the operational intensity is around 8 operations per cycle. So we are in the compute-bound regime, which it should be possible to achieve the 8 gigaflops that we plan. It should be possible. It is theoretically possible. It doesn't mean that it's easy to achieve. The scheduling of the vector instructions is key here, in a way that the memory operations and the compute operations can run in parallel. Those are our results. We achieve around 82% of utilization of the FMAs, or 6.6 operations per cycle. So in the first zone, as before, banking conflicts, the ones we've seen before, and the extra scalar could delimit performance. And in the steady regime, we are pretty much flat at 6.6. Why? It comes back a bit to the whole strip mining loop. Until 256, we can do the convolution in one strip mining iteration. And after this, we actually break the convolution. And it could go a bit higher, but to do this, we would need to unroll the strip mining loop, which would have some effects on the whole programmability of the system. But it's a software problem. And then the final kernel, it's a matrix multiplication. Again, it should be possible to achieve 8 operations per cycle, because the operational intensity here is n over 12 operations per byte. It's a big O of n. So if n is over 12 rows, we are in the compute-bound regime. Again, we are up to 86% utilization of the FMAs, and we see more or less the same phenomena we have seen before with the convolution alone. We see this limitation with shorter vectors, and we see a limitation, a flattening of the performance with longer vectors, bigger matrices, maybe. So can we achieve the 8 gigaflops we said we could? Well, not the 8 gigaflops, but with vectors of length 256, we are actually 10% below the roofline on these compute kernels. And on very memory-bound kernels like the XP, which is in red, we are also not very far from the roofline. With the optimizations we did on the compute-bound, did not destroy the performance of the memory-bound kernels. Now we'll talk a bit about the implementation result. Here is our backend result. Again, GlobalFound's FTX 22 at 1 gigahertz, slow corner. So here we have Arjan in light blue, which amounts to 36% of the area together with the data and instruction caches. And here is ARA, 64% of the area, and there you can see the vector raster file. This is a rough breakdown of the area. If we concentrate just on ARA's side for a moment, you can see that the area is heavily dominated by the execution units and the vector raster file. And also there is quite a bit of area that is dedicated to the operand queues, because they are pretty wide and deep. So ARA is 1.8 times bigger than Arjan. However, it has 4 times more computational power, which means that in terms of operational density, Arjan achieves around a bit more than 7 gigaflops per square millimeters, whereas ARA is a bit more than 16 gigaflops per square millimeters. The critical path is around 45 gates, and they pass through the lower priority request of the vector raster file arbiter. So to wrap up my presentation, some conclusions, some insights. First, the shuffling instructions. As we've seen before, to have a higher operational density on the kernels, it's interesting not to pass through memory. It's interesting to have instructions that allow us to shuffle data, to move data between vector registers. The extension has two instructions for this: vector slide, that slides one source vector by a fixed amount, and vector register gather, that allows for general permutations. The problem with the vector register gather is that it is too general. It's hard to optimize due to how general it is. So we think that it would be interesting to have more specific shuffling instructions, for example, permutations or rotations. Another point is the decoupling between the scalar and the vector unit. We thought this was an interesting design choice, because the scalar and the vector unit, they actually live in different worlds, if I may. So the scalar unit is speculative, has several in-flight operations, has this latch beta register file, whereas in the vector unit, we are in this non-speculative regime, not as many in-flight operations, a register file that is based in SRAMs. So we see with a certain apprehension the direction the ISA seems to be taking to recoupling the vector and the scalar worlds. For example, there's a decision of mapping the vector registers and the floating point registers together. And one final point is the mixed precision. So ADA supports mixed precision to a certain extent. However, in the previous versions of the extension, for example, the version 0.4 that has been used here, it allowed, for example, for this kind of type promotion. You could go from 8 bits source to a 64-bit destination. However, we've seen that the hardware impact of this kind of operation was a bit too costly. And this is why we only support a more restricted set of type promotions, from 8 to 16 bits, from 16 to 32 bits, and from 32 to 64 bits, which is also aligned with newer revisions of the V extension itself. And it's with this that I conclude my presentation. Thanks for listening to me.